Saturn is a cosmic masterpiece hiding a trove of unsolved puzzles. This iconic ringed planet, so familiar in pictures, is home to phenomena that defy our understanding of nature itself. Today, we are going on a journey to uncover 25 of its greatest enigmas. You will discover why a perfect hexagon storms at its north pole, how a small moon shoots ingredients for life into space, and whether those magnificent rings are slowly vanishing before our eyes. We will explore giant hurricanes, disappearing lakes, and moons that swap places in a gravitational dance. By the end, you will see Saturn not just as a beautiful planet, but as one of the most mysterious and active worlds in our solar system. What does it feel like to look at the night sky and know that some of its greatest secrets are still waiting to be found? Among these mysteries, one stands out for its sheer geometric perfection. At Saturn's North Pole, a storm rages in the shape of a perfect hexagon. This is not an artist's impression or a trick of the light. It is a colossal, six-sided jet stream, a hurricane of unimaginable scale that has been spinning for decades, perhaps even centuries. Its discovery was a complete shock to scientists. The Voyager probes first glimpsed it in the 1980s, but the images were grainy and distant. For years, many wondered if it was just a fleeting anomaly. Then the Cassini spacecraft arrived decades later and stared directly into the heart of this storm. The hexagon was not only still there, it was more defined and stable than anyone could have predicted. This structure is so vast that the entire planet Earth could fit inside it, with room to spare. Think about that for a moment. A single weather pattern on another planet is larger than our entire world. On Earth, our atmospheric systems are chaotic and fluid, forming swirling circles or meandering bands. They do not lock themselves into rigid, geometric shapes with razor-sharp 60-degree angles. So, how does Saturn do it? Scientists believe it is a type of standing wave pattern, a kind of atmospheric oscillation trapped at the planet's pole, similar to how a wave can get stuck in a fast-moving stream. But the exact recipe for creating and, more importantly, maintaining such a crisp hexagon for so long remains one of planetary science's greatest puzzles. What force acts as a cosmic mold, shaping a hurricane of gas into a polygon? The hexagon is a silent, spinning monument to all the physics we have yet to understand. That hexagon is a clockwork marvel, a visible heartbeat in Saturn's churning atmosphere. Yet beneath those clouds, the planet's own heart beats to a rhythm we cannot quite hear. Determining the exact length of a Saturnian day, the true rotation rate of the planet's deep interior, has proven to be one of the most stubborn puzzles in modern astronomy. For Earth, this is simple. We watch the sun rise and set, or we plant a flag and watch it spin. But a gas giant has no solid surface to plant a flag on. For decades, the standard method was to listen to the planet's magnetic heartbeat. A planet's magnetic field is generated by churning molten material deep in its core, and as the planet spins, that field wobbles slightly, emitting a radio pulse. By timing that pulse, you can clock the rotation of the planet's hidden interior. This worked perfectly for Jupiter. But Saturn, true to its mysterious nature, broke the tool. Its magnetic field is almost perfectly aligned with its rotation axis. There is no wobble, no discernible pulse to listen to. It is as if the planet's internal compass is locked in place, giving us a silent, unreadable face. So scientists had to get creative. They turned to the planet's magnificent rings, using them as a giant seismograph. Just as earthquakes send tremors through the Earth, vibrations from deep within Saturn travel outward and gently shake its rings, creating spiral patterns. By reading these patterns, researchers could try to sense the planet's internal vibrations and infer its rotation. Others watched cloud features in the atmosphere, tracking giant storms as they whipped around the planet. But these methods told different stories. The rings suggested one rotation period, the clouds another. For years, the fundamental question of how long a day lasts on Saturn had two conflicting answers, separated by about 6 or 7 minutes. That might not sound like much, but on the scale of a planet, it represents a profound gap in our understanding. The final act of the Cassini mission was a daring series of orbits, diving between the planet and its rings. This grand finale provided our best data yet, suggesting a day lasts about 10 hours, 33 minutes, and 38 seconds. But even this is an estimate, a calculation based on the subtle tug of gravity on the spacecraft. The true, definitive rotation of Saturn's hidden heart remains unobserved, a secret the silent giant keeps locked beneath 1,000 miles of swirling cloud. That hidden rotation rate is a fundamental mystery, but Saturn's most iconic feature presents an even deeper puzzle about time itself. The origin and age of those breathtaking rings is a question that has divided planetary scientists for generations. Are we looking at a primordial structure, a fossil from the birth of the solar system 4.5 billion years ago? Or is this a dazzling but temporary spectacle, a cosmic event that unfolded in a much more recent chapter of our solar system story? For a long time, the assumption was that the rings were ancient. It made intuitive sense. Such a magnificent, complex system must have formed alongside Saturn from the great disk of gas and dust that birthed all the planets. But the Cassini mission's close-up observations delivered evidence that shook this idea to its core. The rings are astonishingly bright and clean, composed of nearly pure water ice. In the harsh environment of space, exposed to a constant rain of dark, dusty micrometeorites, anything that old should have become significantly darkened and polluted over billions of years. Their pristine condition suggests they have not been collecting cosmic grime for very long. The data pointed toward a shocking youth. By analyzing how the ring's mass tugged on the Cassini spacecraft during its final daring orbits, scientists calculated their total weight. That mass, lighter than many previous estimates, became a key clue. Combined with models of how rings darken and spread out over time, the evidence now strongly suggests Saturn's rings are a recent masterpiece. The leading theory paints a dramatic picture. Perhaps as recently as 100 million years ago, a medium-sized icy moon or a large comet strayed too close to Saturn. The planet's immense gravity would have torn this visitor apart in a catastrophic event. The shattered debris, captured into orbit, then gradually ground itself down through countless collisions, spreading out into the vast, flat disk we see today. We may be living in a special cosmic moment, witnessing a brilliant but fleeting structure that simply did not exist during the age of the dinosaurs. Yet, some scientists still argue for an ancient origin, proposing complex mechanisms that could continually refresh the ring's surfaces and explain their brightness. The debate continues, making the rings not just a thing of beauty, but a celestial clock we are still learning to read. Their very existence asks us a profound question. Are we seeing a permanent fixture of our solar system, or merely a brilliant flash in the pan, a temporary jewel that future generations of astronomers might never behold? If the rings are a recent and brilliant spectacle, they also host a ghostly phenomenon that comes and goes like a celestial apparition. Scattered across the broad, bright expanse of Saturn's B-ring are dark, radial features scientists call spokes. Picture a bicycle wheel. These spokes are like faint, shadowy lines stretching from the inner part of the ring outward, spinning along with the ring material itself. They are not solid structures, but temporary congregations of incredibly fine, dust-sized particles. For reasons we do not fully understand, these tiny bits of ice become electrically charged, causing them to levitate slightly above or below the flat plane of the rings. This levitation is the key to their visibility. When these dust clouds float above the main ring layer, the sun shines on them at a different angle, casting shadows that make them appear dark against the bright rings below, or sometimes bright against a darker background. It is a delicate dance of light and shadow happening on a scale of thousands of miles. Their behavior is deeply strange. The spokes are not permanent. They form, stretch, and fade away over a few hours. Even more intriguing, they seem to follow a seasonal pattern, appearing more frequently and prominently in the periods around Saturn's equinoxes, when the sun shines directly on the ring plane. This seasonal clue is a vital hint. One leading theory suggests that during equinox, the angle of sunlight allows for stronger electrostatic forces to build up. Perhaps the dust is charged by plasma in Saturn's magnetosphere, the planet's giant magnetic bubble, causing the particles to repel each other and float away. Another idea points to meteoroid impacts. A tiny strike on the rings could blast a cloud of dust upward, with the resulting debris then becoming charged and behaving like a spoke. The Cassini spacecraft witnessed these events in stunning detail, watching them form and dissipate like weather patterns. Yet the exact trigger, the precise combination of magnetic influence, solar angle, and ring particle composition that conjures these spectral shapes, remains an active mystery. They are a reminder that Saturn's rings are not a static painting, but a dynamic, almost living system where invisible forces paint temporary masterpieces across the ice. While the rings host temporary patterns, one of Saturn's moons wears a permanent and startling mask. Iapetus is a world of pure contrast, a celestial yin and yang. One half of this moon is as dark as fresh asphalt, a deep reddish black, while the other half gleams with the brilliant whiteness of clean snow. This stark divide is not a trick of shadow, but its actual two-toned surface. The leading hemisphere, the face that plows forward as Iapetus orbits Saturn, is coated in that mysterious dark material. The trailing hemisphere, meanwhile, is almost pure water ice. How does such an extreme color split happen? For a long time, the prime suspect was an external source. Scientists looked outward to another of Saturn's distant dark moons, Phoebe. Phoebe orbits in the opposite direction, and it is constantly bombarded by tiny impacts, kicking up a faint haze of dark dust. The theory went that this dust slowly spirals inward toward Saturn, and Iapetus, on its journey, simply sweeps it up like a cosmic windshield collecting bugs on a highway. The dark coating would then absorb sunlight, warming that side of the moon just enough to trigger a runaway process. The heat would cause any exposed ice on the dark side to sublimate, turning directly from solid to vapor. This vapor would then drift across the moon and refreeze on the colder, brighter trailing hemisphere and poles, making the dark areas even darker and the bright areas even brighter. It is an elegant idea, but recent data has introduced a compelling alternative. What if the dark material is coming from within Iapetus itself? Some scientists now propose it could be the result of ancient cryovolcanism, where the moon once spewed out a sludge of dark organic compounds mixed with water, painting its own face in a process of self-brutalization. This internal theory gains intrigue when you look at Iapetus's other bizarre feature. Running perfectly along its equator is a monstrous ridge, a chain of mountains over 12 miles high that makes the moon look like a giant cosmic walnut. This ridge is so precise it seems artificially drawn. Could the same internal forces that created the ridge also have belched forth the dark material? Perhaps the ridge formed from a time when Iapetus spun much faster, and material welled up from its interior and froze in place, with some of that material being dark and tarry. The connection between the two-toned face and the equatorial belt remains one of the great unsolved puzzles of the Saturnian system. Iapetus stands alone, a stark reminder that even familiar categories like moon can produce something utterly alien and inexplicable. From a moon painted in permanent shadow and light, we turn to one that actively paints its own future against the blackness of space. Enceladus is a small, icy world, barely 300 miles across, that should be a frozen, geologically dead relic. Instead, it is one of the most active places in our solar system. At its south pole, a series of massive fractures, nicknamed the tiger stripes, scar the surface. From these deep wounds, enormous plumes of water vapor and ice crystals erupt into space at supersonic speeds, creating a shimmering halo around the moon and feeding one of Saturn's outer rings. The Cassini spacecraft did not just observe these geysers from a safe distance. It performed one of the most daring maneuvers in the history of exploration. On multiple passes, Cassini dove directly through the plumes, its instruments tasting and analyzing the spray. What it found rewrote the book on where to look for life. The geysers were not just simple water ice. They were rich in sodium salts, like those found in Earth's oceans. They contained simple organic compounds, the carbon-based building blocks of all life as we know it. Most tellingly, they held tiny particles of silica, a mineral that on Earth only forms in liquid water that is in contact with hot rock. This was the smoking gun. Enceladus was not just venting surface ice, it was venting the contents of a vast, global subsurface saltwater ocean. And that ocean was not a frozen block, but a warm, churning body of water, heated from below by hydrothermal vents on the ocean floor where the hot, rocky core of the moon meets the water. This is a monumental discovery. On Earth, in the absolute darkness of our own deep ocean floors, hydrothermal vents are thriving oases of life. The heat and minerals they provide support entire ecosystems that exist completely independent of sunlight. Enceladus has recreated this exact recipe hundreds of millions of miles from the sun. It possesses liquid water, a source of chemical energy from the hydrothermal activity, and the essential organic building blocks. This small moon now sits at the very top of the list of places in our solar system that could harbor life. The central, breathtaking mystery is no longer if Enceladus has an ocean, but what is swimming in it. We do not yet know the exact chemistry of that hidden sea, how long it has been stable, or precisely how much energy its vents provide. Future missions may one day fly through the plumes with more sensitive instruments, searching for complex organic molecules or even signs of biological processes. For now, Enceladus stands as a profound promise, a tiny, icy shell hiding a world of liquid potential and whispering a single, compelling question into the void. The discovery of that hidden ocean was just the beginning. The true revelation came when scientists analyzed the chemical signature of those icy geysers and found something extraordinary: molecular hydrogen. This simple molecule, just two hydrogen atoms bonded together, is like a high-energy snack for certain microbes. On Earth, in the sunless depths of our oceans, life thrives around hydrothermal vents, not by photosynthesis, but by chemosynthesis. Microbes there use the hydrogen sulfide or hydrogen bubbling from the vents, combining it with carbon dioxide dissolved in the water to create the organic matter that forms the base of an entire food web. Finding a rich supply of molecular hydrogen in Enceladus's plumes is a powerful clue. It tells us that deep on the moon's seafloor, hot water is reacting with rocks, a process called serpentinization. This is not a gentle simmer. It is a sign of intense hydrothermal activity, where mineral-rich water, heated by the moon's core, is surging through a rocky seabed and emerging loaded with chemical energy. The presence of tiny, perfectly round silica nanoparticles in the plumes confirmed this picture. On Earth, these specific particles only form in very hot water above 200 degrees Fahrenheit, that is in prolonged contact with rock. Enceladus was giving us a direct sample of its ocean floor, and it was screaming that the conditions for life as we know it are not just possible, they are actively present. This transforms the moon from a curious place with water into a potentially habitable world. The dark, cold ocean is not a sterile void. It is a chemical reactor, continuously fueled by heat from below. It has all the key ingredients, liquid water, organic building blocks, and now a clear, abundant source of chemical energy. So the question shifts from could life exist to what might that life be like? In the perpetual darkness, under the crushing pressure of miles of ice, any life would likely be microbial, similar to the extremophiles clustered around Earth's own vents. Perhaps it would be simple, single-celled organisms that harvest energy from the hydrogen and methane in the vent fluids. But given the stability of this environment over perhaps billions of years, who is to say what complexity could have evolved in that isolated, watery world? Could there be filter-feeding organisms clinging to rocky outcrops near the warmth? Or even free-swimming creatures in the darker, colder waters above? We have no way of knowing, but the mere possibility that we are looking at a second genesis of life in our own solar system, hidden beneath the ice of a small gleaming moon, is a thought that redefines our place in the cosmos. While Enceladus hides a warm, saltwater ocean, another of Saturn's moons presents a surface so familiar it feels like a distorted mirror of our own world. Titan is the only moon in our solar system with a substantial atmosphere and the only other place we have found stable liquid on its surface. But this is not the water of Earth. On Titan, with surface temperatures plunging to minus 290 degrees Fahrenheit, water is frozen harder than granite. Instead, the rivers that carve valleys, the waves that lap at shorelines, and the vast seas that sprawl across the landscape are composed of liquid methane and ethane. These are hydrocarbons, the components of natural gas, flowing as freely as water does here. It is an eerily Earth-like landscape built from utterly alien chemistry. The Cassini mission and its Huygens lander gave us our first clear view of this strange hydrologic cycle. Clouds of methane gather in a hazy orange sky, rain falls in slow-motion droplets, and that rain collects into streams that feed deep lakes and seas. Yet the distribution of this liquid is a puzzle in itself. Nearly all of Titan's large liquid bodies are clustered at its north pole, with a few smaller lakes in the south. Why is the north so wet while much of the equatorial region is a vast, dry dune sea of hydrocarbon sand? Scientists suspect this unevenness might be driven by Titan's long, eccentric seasons, each lasting about 7 Earth years. As the moon orbits Saturn, the intensity and location of sunlight shifts over decades-long cycles, potentially causing methane to evaporate from one hemisphere and condense in the other over vast timescales. The lakes themselves hold bizarre secrets. Radar images from Cassini revealed transient features dubbed magic islands. These are bright patches that appear in the seas on one flyby, only to vanish by the next. They are not permanent land masses. The leading theories suggest they could be waves, clusters of bubbles rising from the seafloor, or even floating solids like porous hydrocarbon icebergs. Imagine a slab of frozen organic material, lighter than the liquid methane sea, bobbing to the surface and then slowly dissolving or sinking again. The shorelines of these seas are another enigma. Some appear sharp and defined, while others are diffuse and marsh-like, suggesting the liquid methane might be slowly seeping into the surrounding bedrock of water ice, creating a sodden, porous border. The largest sea, Kraken Mare, is a monster. Larger than Earth's Caspian Sea, its depth remains uncertain, but estimates suggest it could be over 1,000 feet deep in places. A vast, dark reservoir of liquid hydrocarbons. All of this points to a hydrocarbon cycle of stunning complexity, a full weather system with evaporation, cloud, formation, precipitation, and surface flow, but operating with a completely different set of rules and ingredients. This raises the most profound question of all. On a world with such active chemistry and abundant organic molecules, could this liquid environment support a form of life that does not rely on water? Astrobiologists speculate about the possibility of exotic methane-based life forms, organisms that use liquid methane the way we use water as a solvent for their biological processes. While this remains highly speculative, Titan stands as a testament to nature's boundless creativity, proving that the recipe for a dynamic, world-shaping cycle can be written in more than one language. That alien landscape is wrapped in an even greater enigma. Titan's atmosphere is thicker than our own, a dense orange shroud that exerts more pressure at its surface than the air at sea level on Earth. This is baffling. Titan is only 40% larger than our moon, a body that is essentially airless. By all rights, Titan should not be able to hold on to such a massive blanket of gas. Its gravity is too weak, and it sits within the reach of Saturn's powerful magnetic field, which should help strip away any atmosphere over time. So how does this little moon defy physics and keep its sky? The answer seems to be a delicate, ongoing balance between loss and supply. Titan's atmosphere is mostly nitrogen, just like Earth's, with a significant amount of methane. These gases are constantly leaking into space, a slow but steady trickle of molecules escaping Titan's weak gravitational grip. For the atmosphere to persist over billions of years, something must be actively replenishing the loss. Scientists believe the methane, and possibly other gases, are being steadily released from within Titan itself, a process called outgassing. This suggests a geologically active interior with reservoirs of liquid or clathrates, icy cages that trap gas molecules, slowly warming and releasing their contents to the surface. It is a global system where the moon breathes, exhaling gases from its interior to replace what the vacuum of space steals away. This internal activity is what makes the atmosphere so dynamic. High above the surface, sunlight and energetic particles smash into the methane and nitrogen, triggering a cascade of complex chemical reactions. This creates a thick photochemical haze of organic compounds, a smog of hydrocarbons like ethane and propane, and even more complex molecules that rain down on the surface. This continuous organic drizzle is why Titan's surface is covered in dunes of hydrocarbon sand and filled with lakes of methane. The atmosphere is not just a blanket. It is a giant, planet-sized chemistry lab, manufacturing the very ingredients that shape the moon's geology. The enduring mystery is the exact source and mechanism of this replenishment. Are there cryovolcanoes periodically erupting with slushy mixtures of water, ammonia, and methane, puffing fresh gas into the sky? Or is the outgassing a slower, more widespread seepage from a global reservoir just beneath the icy crust? Understanding this balance is key to unraveling Titan's entire history. Its thick atmosphere is a living record, a sign that this cold, distant moon is far from dead. It is a world with a hidden, churning heart, one that actively maintains its own alien sky against all odds, and in doing so, paints its surface with the building blocks of something truly extraordinary. Titan's thick atmosphere is a masterpiece of persistence, but Saturn's family also includes a moon that seems to defy the very concept of structure. Hyperion is a cosmic sponge. This small, potato-shaped moon, only about 250 miles across, looks like it has been blasted by a celestial shotgun. Its surface is a chaotic jumble of deep, sharp-edged craters with dark material pooled at their bottoms, giving it an eerie, porous appearance. But the strangeness is more than skin deep. Hyperion has an extremely low density, about half that of water. This means it cannot be a solid ball of rock and ice. Instead, it must be mostly empty space, a fragile, loosely bound pile of rubble, where the gaps between chunks might be larger than the chunks themselves. It is a celestial Swiss cheese, so porous that if you could stand on its surface, you might sink into a labyrinth of caverns and voids. This bizarre composition leads to its other weird behavior, a chaotic, tumbling rotation. Unlike our moon, which shows us only one face, Hyperion spins unpredictably. Its axis of rotation wobbles so violently that its day length and the orientation of its poles are essentially impossible to predict. There is no steady rhythm, only a drunken stagger through space. This is a direct result of its irregular shape and the gravitational kicks it receives from its massive neighbor, Titan. Every time Hyperion has a close encounter with Titan, the larger moon gives it a gravitational nudge, changing its spin in a random way. It is a moon without a stable sense of up or down. The question is, how did such a fragile object even form and survive? The leading theory points to a violent past. Hyperion is likely a remnant of a catastrophic collision that occurred early in the solar system's history, a fragment that was never pulled together by its own gravity into a compact sphere. It is a rubble pile that was never packed down. But why hasn't Saturn's immense gravity, over billions of years, finally crushed this delicate structure into something more solid? The answer might lie in its composition. Hyperion appears to be made primarily of water ice, which is surprisingly strong at the cold temperatures of the outer solar system. This icy framework might provide just enough structural integrity to resist total collapse, like a house of cards made from frozen, rigid material. Its very existence challenges our ideas about how celestial bodies hold themselves together. Hyperion is not a world, but a fossilized avalanche, a snapshot of chaos frozen in time, tumbling endlessly in an orbit it can never quite control. This delicate cosmic rubble pile is a testament to chaos, but Saturn also orchestrates a dance of perfect precision. Two small moons, Janus and Epimetheus, perform a gravitational ballet so elegant it seems choreographed. They travel along orbits so nearly identical that for years, astronomers believed they were a single object. Yet these are two distinct worlds, separated by only about 30 miles in their orbital paths, a hair's breadth in celestial terms. This should be a recipe for disaster. Two bodies sharing the same highway around a planet will inevitably either collide or fling each other into wildly different paths. But Janus and Epimetheus have found a third option, a stable, repeating loop that defies that violent fate. Every 4 Earth years, the inner moon, which orbits slightly faster, begins to catch up to its outer companion. As they approach, their mutual gravitational pull becomes significant. Instead of crashing, they perform a graceful exchange. The inner moon tugs the outer moon inward, giving it a bit of energy. The outer moon, in turn, slows the inner moon down, stealing some of its momentum. This trade causes them to swap places. The moon that was ahead falls behind, and the moon that was behind moves ahead. They then begin to drift apart again, only to repeat the entire process 4 years later. If you could trace their paths relative to each other from Saturn's perspective, it would not look like two circles, but a single intertwined horseshoe. Each moon travels along one arm of this horseshoe, approaching the shared point from opposite ends, exchanging places, and then moving away again along the other arm. It is a timeless clockwork maneuver, a celestial do-si-do governed by the immutable laws of gravity. The profound mystery is how this dance began. Did these two moons form together from the rings or from the debris of a larger, shattered moon, their orbits fine-tuned from the start? Or are they captured objects, strangers that wandered into Saturn's gravitational influence and somehow settled into this miraculously stable resonance? Their nearly identical size and composition suggest a common origin, perhaps fragments of a single parent body that broke apart and then, through countless gentle interactions, settled into this harmonious rhythm. Their dance is a beautiful puzzle, a demonstration that in the vastness of space, chaos can give birth to an enduring and delicate order. That delicate gravitational dance is a masterclass in celestial harmony. Yet Saturn's rings host a spectacle of beautiful chaos. The F-ring is a wild frontier, a thin, eccentric band of ice and dust that behaves like nothing else in our solar system. It is the outermost of Saturn's main rings, a delicate strand, no more than a few hundred miles wide, but within that narrow corridor, an entire universe of activity unfolds. This is not a serene disk of orbiting ice. It is a constantly shifting, kinked and braided stream, a ring that looks as if it has been woven by invisible hands and then violently shaken. The architects of this chaos are two small shepherd moons, Prometheus and Pandora. These moons orbit on either side of the F-ring, and their gravitational influence is relentless. Prometheus, the inner shepherd, is the primary troublemaker. Its orbit is slightly elliptical, bringing it swooping close to the inner edge of the ring every 17 hours. As it approaches, its gravity reaches out like a cosmic finger, dragging tendrils of icy material from the ring's core. These pullouts create spectacular streamers, long filaments of debris that can stretch hundreds of miles across the ring's face. Sometimes the material is pulled so forcefully it forms temporary knots and clumps that shine brightly before being stretched apart again. Pandora, the outer shepherd, exerts its own influence, often confining the material Prometheus has stirred up, adding to the dynamic tension. The result is a ring that changes visibly from one Cassini spacecraft flyby to the next. You can literally watch it evolve. Beyond the shepherd's direct tugs, the ring particles themselves are in a constant state of low-grade collision. These gentle crashes create jets of material, bright outbursts that appear as if the ring itself is sprouting new features. Some of these clumps can be miles across and persist for months, acting like miniature moons within the ring itself. The central mystery is not that these interactions happen, but why they produce such a staggering variety of structures. The physics of countless tiny, icy particles, each responding to the gravity of two moons and their own mutual collisions, creates a system of mind-boggling complexity. Scientists use sophisticated computer models to simulate the F-ring, but reproducing every braid, every kink, and the lifespan of every persistent clump remains a formidable challenge. It is a real-time laboratory for orbital dynamics, a place where the fundamental forces that build solar systems are playing out in fast-forward right before our eyes. While the F-ring is a tapestry of gravitational chaos, Saturn's poles are dominated by storms of terrifying order. At both the North and South poles, the planet hosts permanent, hurricane-like vortices of staggering scale. These are not the fleeting cyclones of Earth, but locked, raging maelstroms that have likely churned for centuries. The southern vortex was the first to be seen clearly, a vast storm with a distinct, cloud-free eye, reminiscent of a hurricane but on a planetary scale. The North Pole, of course, is famously crowned by the hexagon, but within that geometric jet stream lies its own violent vortex. The sheer size of these storms defies comprehension. The eye walls, the rings of towering clouds that surround the calm center, soar up to 40 miles high. That is over 5 times the height of Mount Everest. If such a storm formed on Earth, its clouds would punch through the stratosphere. They persist year-round, unaffected by the changing seasons that dictate weather on our world. This endurance presents the first major puzzle. On Earth, hurricanes are heat engines. They draw their ferocious power from the warm, moist air over tropical oceans. The ocean acts as a fuel tank, and when a storm moves over land or cold water, it starves and dissipates. Saturn has no liquid surface to speak of. There is no warm ocean beneath those clouds to feed the storm's engine. So what is the power source? The answer seems to lie within Saturn itself. These polar vortices are not surface weather. They are likely manifestations of energy rising from deep within the planet's atmosphere. Saturn radiates more than twice the heat it receives from the Sun. This internal warmth, left over from the planet's formation and possibly from helium raining down into its core, drives colossal convection currents. Imagine a pot of water boiling on a stove. Hot fluid rises from the bottom, cools at the surface, and sinks back down, creating circulating cells. On a planetary scale, this churning may be funneled and focused at the poles by Saturn's rapid rotation and its unique global wind patterns, creating these permanent, self-sustaining storms. The vortexes are not just powered from below, they're also strangely warm at their hearts. Infrared measurements reveal that the air at the very center of these polar storms is significantly warmer than the surrounding atmosphere by dozens of degrees. This is the opposite of a terrestrial hurricane, where the eye is calm but composed of cooler, sinking air. Saturn's warm cores suggest a different mechanism. The air in the eye may actually be sinking, but as it descends from the extremely high altitudes of the eye wall, it compresses and heats up like the air in a bicycle pump. This creates a localized hot spot locked in the storm's center. These vortices are more than just spectacular storms, they are windows. By studying their structure and heat signatures, scientists can infer the complex, deep circulation patterns of Saturn's entire atmosphere. They are the visible tops of planet-sized convective chimneys, where the hidden heat of Saturn's interior finally erupts into view. The mystery is in the details, how exactly the planet's internal furnace, its furious spin, and its global weather patterns conspire to forge and cage these perfect perennial hurricanes at the very ends of its world. The heat from those polar vortices hints at the churning chemistry deep within Saturn, but the planet's very atmosphere holds a fundamental mismatch. Compared to its giant sibling Jupiter, Saturn has a surprising lack of methane. Based on our understanding of how gas giants form from the primordial solar nebula, the ratio of methane to hydrogen and helium should be fairly similar for both planets. They are, after all, made from the same basic soup of cosmic ingredients. Yet when scientists measure Saturn's atmosphere, they find its methane is significantly more scarce. This is not a minor discrepancy. It is a glaring clue that something about Saturn's story is different. A compositional mystery written in the very air of the giant. One compelling theory points to birthplace. Perhaps Saturn formed farther out in the cooler reaches of the young solar system, in a region where temperatures were low enough for methane to freeze onto dust grains as solid ice. If those icy grains then clumped together to form the planet's solid core, a great deal of the available methane would have been locked away inside Saturn from the very beginning, buried too deep to mix into the outer gaseous envelope we see today. Another possibility involves an internal journey. Saturn's intense internal pressure and heat might be driving a process that destroys or transforms methane in its deep atmosphere. Some models suggest that under the extreme conditions near Saturn's core, methane could break apart, with its carbon reacting to form other compounds, like diamonds that rain down into the interior. Imagine a world where it literally rains diamonds in the deep, a process that would steadily deplete the upper atmosphere of its methane over billions of years. There is also the chance that Saturn experienced a different kind of formation history altogether, one involving a colossal impact that stripped away a portion of its original atmosphere, altering its chemical fingerprint forever. This missing methane is far more than a chemical curiosity. It is a direct tracer of the planet's deepest history, from its birth location and temperature to the violent events that may have shaped its youth. By solving this atmospheric puzzle, we are not just accounting for a gas. We are reading the first chapter of Saturn's biography, written in elements it either kept, lost, or buried within its heart. The missing methane points to a hidden interior, but Saturn's atmosphere unleashes its buried energy in a far more violent spectacle. Across the planet's cloud decks, lightning storms of almost unimaginable power erupt, generating bolts thousands of times stronger than anything on Earth. We cannot see this lightning with ordinary cameras, as it flashes deep within the thick, opaque atmosphere. Instead, we listen to it. The Cassini spacecraft detected these events as bursts of intense radio noise, crackling pops and hisses dubbed Saturn electrostatic discharges. Each burst is the signature of a colossal electrical discharge happening hundreds of miles below the visible cloud tops. The energy involved is staggering. A single Saturnian lightning bolt could power every city on our planet for a year. The sheer scale forces us to re-imagine what a thunderstorm can be. On Earth, lightning is born from the collision of ice particles and water, droplets within towering cumulonimbus clouds. Saturn's recipe must be utterly different, as its clouds are made of ammonia, ammonium hydrosulfide, and water vapor, churning in an atmosphere of mostly hydrogen and helium. The exact mechanism that separates enough electrical charge to create such titanic sparks remains a key mystery. Do massive blizzards of ammonia, ice crystals, collide in deep convective towers? Does a form of precipitation we cannot yet imagine, perhaps helium rain or diamond hail, drive the charge separation? The depth of these storms is another puzzle. The radio signals suggest they originate far beneath the upper cloud decks, in a hidden layer where water may finally condense. This implies a world of weather operating on a scale we can only infer, with storm cells so vast they would engulf continents. Among these electrical monsters, one event stood out so dramatically it earned its own name, the Dragon Storm. This was not a fleeting flash, but a giant, long-lived, convective beast that raged for months. Cassini's radio and plasma wave instrument tracked its furious radio chatter, while its cameras eventually spotted the bright, complex cloud feature associated with it churning in the mid-latitudes. The Dragon Storm was a massive, turbulent upwelling of warm air from Saturn's deep interior, punching through the colder upper atmosphere and unleashing a continuous barrage of super bolts. Its persistence is as puzzling as its power. Most convective storms on Saturn, like the famous Great White Spots, erupt and then fade as they dissipate their energy. The Dragon Storm somehow maintained its fury, suggesting it tapped into a particularly deep and stable source of warm, moist air, a plume from Saturn's hidden meteorological engine that refused to be capped. Visualizing these events stretches the imagination. Picture a flash so brilliant it momentarily outshines the rest of the planet's sunlit side, a blue-white fork hundreds of miles long, illuminating thousands of miles of swirling ammonia cloud canyons from within. The thunderclap from such a bolt, if sound could travel through space, would be a roar to silence all others. These storms are more than just atmospheric fireworks. They are probes. By studying their radio fingerprints and the heat signatures of the cloud outbreaks they produce, scientists can map the vertical structure of Saturn's atmosphere, sensing the layers of wind, temperature, and composition that are otherwise forever hidden from our view. Each crackle is a message from the deep, a violent testament to the turbulent, energetic, and still largely unknown forces churning within the ringed giant. Deep within the organized lanes of Saturn's A-ring, a gentler kind of sculpting is at work. Here, hidden moonlets no bigger than a city, perhaps only half a mile across, are carving their own signatures into the ice. We cannot see these tiny worlds directly, but their effects are unmistakable. As they orbit within the ring plane, their gravity is just strong enough to push the fine ring particles aside, but not strong enough to clear a complete gap. The result is a distinctive propeller-shaped disturbance. Two partial S-shaped gaps open up in the ring material ahead of and behind the moonlet, while the tiny world itself sits at the center like the hub of a celestial gear. The Cassini spacecraft spotted thousands of these features, giving them nicknames like Blériot and Earhart after pioneering aviators. They are not static monuments. Over years of observation, Cassini watched individual propellers move, tracing their orbital paths and even spotting some that seemed to migrate slightly over time. This is where the mystery becomes profound. These propeller moonlets are essentially baby planets caught in the act. They are the smallest kind of building block, an object massive enough to start clearing its immediate neighborhood within the disk of material, just as the planets did in the early solar system. But they are trapped within Saturn's immense gravity well, forever held in check, unable to grow into full-fledged moons. Their very existence raises fundamental questions. Where did they come from? One possibility is that they are the shattered remains of a larger moon that was torn apart by Saturn's tides long ago, and these are the surviving fragments. Another, more thrilling idea is that they are still accreting, still gathering ring particles to themselves in a slow motion process of growth that we are witnessing in real time. If that is true, then we are watching planet formation in a miniature, frozen laboratory. Their ultimate fate is another puzzle. Will they eventually migrate through the rings, perhaps spiraling inward or being ejected? Or will they remain as permanent, embedded fixtures, forever hinting at a process of creation that never reached its conclusion? Each propeller is a time capsule and an experiment, a whisper from the era when all worlds were born from disks of dust and ice. Saturn's internal heat fuels those spectacular storms, but the distribution of that warmth across the planet is strangely lopsided. For decades, data from spacecraft and Earth-based telescopes have revealed a persistent and puzzling trend. Saturn's southern hemisphere is consistently warmer at its upper cloud levels than the northern hemisphere. This is not a small difference, but a significant thermal asymmetry that defies simple expectations for a giant ball of gas spinning rapidly in space. The key to unraveling this mystery lies not within the planet, but above it, in the magnificent rings and the slow march of seasons. Saturn's tilt is similar to Earth's, meaning it experiences seasons as it orbits the Sun. But one season on Saturn lasts over 7 Earth years. For more than 7 years, one hemisphere basks in constant summer sunlight, while the other languishes in the long, deep chill of winter. This extreme seasonal cycle drives a massive transfer of energy from the sunny south to the shadowed north. However, the rings add a dramatic complication. They cast a profound shadow onto the planet's northern hemisphere during its summer. Think of a parasol on a cosmic scale. Just when the north should be receiving its strongest, most direct sunlight to warm it up, the rings block a substantial portion of that light, creating a cooling band that wraps around the planet. This ring shadow is not a sharp line, but a deep, wide swath of shade that can lower temperatures in the upper atmosphere significantly. The ongoing puzzle is that the observed temperature difference is more complex than a simple equation of sunlight minus shadow. The atmosphere does not passively accept these conditions. It reacts, circulates, and redistributes the heat in ways we are still trying to map. Giant jet streams and planet-wide circulation patterns act as a global heating and cooling system, moving warm air from the summer hemisphere toward the winter pole. But the rings disrupt this flow. The shadow may be suppressing certain atmospheric waves or altering wind patterns, creating a kind of thermal dam that traps warmth in the south. Furthermore, the composition of the atmosphere itself plays a role. The cooling effect of the ring shadow might encourage certain gases to condense into ice clouds at different altitudes, changing how much sunlight is absorbed or reflected. It is a three-dimensional puzzle of radiant energy, fluid dynamics, and chemistry. Scientists use sophisticated global climate models similar to those for Earth but adapted for a hydrogen giant with a ring parasol to simulate this interplay. The challenge is getting the virtual Saturn in the computer to match the real Saturn we observe. The models must account for the depth of the shadow, the planet's internal heat rising unevenly, and the lag time as the massive atmosphere slowly responds to seasonal changes. This temperature asymmetry is more than a weather statistic. It is a diagnostic tool, a global thermometer reading that helps us reverse engineer the workings of Saturn's entire atmospheric engine. By figuring out why one half of the planet is warmer, we learn how energy flows, stalls, and transforms within an alien sky where a breathtaking celestial ornament also acts as a fundamental climate control. That global temperature puzzle is a surface symptom of the immense energy churning deep within Saturn, an energy that originates from its very heart. The composition and nature of Saturn's core is a foundational mystery, one that holds the key to the planet's birth and structure. Based on our best models of planetary formation and the subtle wobbles in Cassini's trajectory, we can sketch a likely picture. At the center of the gas giant, buried under thousands of miles of crushing metallic hydrogen, lies a dense core with a mass perhaps 15 to 20 times that of our entire planet. This is not a simple ball of iron like Earth's core. Instead, it is thought to be a mixture of rocky material and ices, water, methane, and ammonia, compressed under unimaginable pressure into exotic, hot states we can scarcely replicate. Yet this sketch is frustratingly vague. Is this core a distinct, solid sphere with a sharp boundary, like a peach pit suspended in the middle of the planet? Or is it a diffuse, gradually dissolving mixture of heavy elements that bleeds into the surrounding hydrogen envelope, more like a dollop of thick syrup slowly mixing into a drink? Cassini's grand finale orbits were designed in part to answer this. By measuring precisely how Saturn's gravity tugged on the spacecraft, scientists could map the distribution of mass inside the planet. The results were both revealing and perplexing. They confirmed the core is massive, but suggested it is not a compact, neat sphere. The data points toward a fuzzy core, one that extends out to perhaps 60% of the planet's radius, with heavy elements mixed much farther up into the surrounding layers than anyone predicted. This blurry boundary challenges our basic ideas of how gas giants settle after formation. It implies that the primordial core might have been partially dissolved or stirred up by violent convection over billions of years. The heavy elements, the rocks and ices that first clumped together to give Saturn its gravitational anchor, may still be raining down through the interior in a slow, eternal drizzle. This has profound implications. The core's size and sharpness are direct records of the planet's earliest history. A distinct, solid core suggests a relatively calm formation where the heavy materials settled neatly before the vast gas envelope was captured. A fuzzy, extended core hints at a more chaotic and energetic youth, perhaps involving colossal impacts with other embryonic planets that stirred the deep interior into a murky soup. Understanding this hidden heart is not just about Saturn. It is about decoding the recipe for all gas giants. The way heavy elements are distributed inside a planet tells us about the conditions in the early solar system, how quickly these worlds grew, and what violent processes shaped their infancy. Until we can send a probe that survives the journey to those impossible depths, Saturn's core remains a ghostly presence, a massive, hidden engine whose true shape is the blurred signature of creation itself. That hidden, fuzzy core is a relic of Saturn's violent birth, but a far gentler form of destruction is happening right now, high above the clouds. Saturn is slowly consuming its own rings. A steady drizzle of charged ice particles, known as ring rain, is falling from the rings into the planet's upper atmosphere, following invisible pathways carved by magnetic fields. This phenomenon was first suspected decades ago when astronomers noticed something odd about Saturn's ionosphere, the layer of electrically charged gas high in its atmosphere. It was strangely hazy and varied in density in ways that could not be explained by sunlight alone. The culprit, it seemed, was an influx of material from above. The Cassini mission's final, daring orbits provided the definitive proof. As the spacecraft dove through the gap between the planet and its rings, its instruments were bombarded by a shower of tiny particles, ice and organic compounds streaming inward from the ring plane. This was not random debris, it was a structured flow. Saturn's magnetic field acts like a cosmic highway system. Charged particles of ice and dust within the rings get caught on these field lines, which then funnel them downward toward the planet's magnetic poles. Imagine a planet using its own invisible force field as a straw to sip from its rings. The mysteries surrounding this rain are profound. First, how fast is it falling? Scientists are still trying to quantify the exact rate of mass loss. Is it a light sprinkle or a heavy downpour on a planetary scale? This rate directly impacts our estimates for the ring's total lifespan. If the rain is heavy, it could be a primary mechanism for the ring's eventual disappearance, supporting the theory that they are a relatively young and temporary feature. Second, what is this rain made of? The particles are not pure water ice. Cassini detected a mix of water, silicates, and simple organic molecules. This chemical cocktail is being injected directly into Saturn's high atmosphere, where it must influence the local chemistry. The influx of water, for instance, could be quenching chemical reactions or forming new types of high-altitude clouds. Finally, what effect does this constant influx have on the planet itself? The energy carried by these falling particles, even if they are tiny, must heat the upper atmosphere at the poles. This could explain some of the unusual auroral and temperature patterns observed there. The rings are not just a passive decoration, they are an active participant in Saturn's atmospheric system, seeding it with foreign material in a slow, cosmic weather pattern. The rings are giving themselves to the planet in a silent, magnetic rain that may one day leave Saturn bare. This gentle rain from the rings is a slow erasure, but on Enceladus, the entire surface is being rewritten in a far more dramatic fashion. The moon's face tells a story of perpetual youth, while other icy moons are pockmarked with ancient craters. Vast plains on Enceladus, particularly around its active south pole, are eerily smooth. It is a landscape that looks freshly paved, with few impact scars to record billions of years of history. This smoothness is not an accident of composition. It is a clear geological statement. Something is actively erasing the past, filling in the craters and smoothing out the rough edges on a global scale. The tiger stripes are just the most obvious vents in this system. The entire region is crisscrossed by fractures and ridges, signs of immense tectonic forces, stretching and pulling the icy crust apart. The driving engine for all this activity is the relentless gravitational tug-of-war with Saturn. Enceladus does not orbit in a perfect circle. Its path is slightly elliptical, meaning its distance from Saturn changes constantly. As it moves closer, Saturn's gravity squeezes it more tightly. As it moves farther away, that grip relaxes. This rhythmic flexing, called tidal heating, generates tremendous friction deep inside the moon's core. Think of repeatedly bending a metal coat hanger back and forth. The point where it bends gets hot. Enceladus is that coat hanger on a planetary scale, being flexed by Saturn's gravity, and that internal heat is what keeps its global ocean from freezing solid and powers the geological violence at the surface. The central puzzle is one of scale and timing. How does a moon only 300 miles across maintain enough internal heat to drive such extreme continuous renewal? The answer may lie in a delicate orbital resonance with another moon, Dione. This gravitational partnership keeps Enceladus's orbit elliptical, preventing it from settling into a circular path that would turn off the tidal heating. It is a perfect feedback loop. The resonance maintains the heat. The heat maintains the ocean and the geological activity, and that activity continually resurfaces the moon, wiping its slate clean. The smooth plains are not just a curiosity, they are a live readout of the moon's internal power. They tell us this is not a world that cooled off long ago. It is a world in a state of constant, churning rebirth, where the icy crust is thin enough and mobile enough to be recycled. Every smooth plane is a page that has been erased, ready for the next chapter of geological activity to be written upon it. What stories of unseen upheavals, of ancient seas that may have breached the surface, have already been lost to this endless renewal? The constant rebirth of Enceladus is orchestrated by the steady pull of Saturn, but the planet itself leans into its orbit with a permanent slant. Saturn's axis is tilted by about 27 degrees, nearly the same angle as Earth's. This simple fact creates a profound similarity between our two worlds, as both experience the rhythmic march of seasons, with sunlight shifting from hemisphere to hemisphere over the course of a year. Yet for a colossal gas giant, this tilt presents a monumental puzzle. How does a spinning ball of gas, over 8 times wider than Earth, end up leaning so dramatically? The leading theory for decades has pointed a finger outward, toward another giant. Early in the solar system's chaotic youth, Saturn may have fallen into a gravitational resonance with Neptune. Imagine the two planets as immense pendulums swinging in a precise rhythm. This linked dance could have gradually torqued Saturn's orientation, pulling its axis over until it settled into its current, pronounced tilt. This explanation paints the slant as an ancient fossil, a relic of planetary billiards from over 4 billion years ago. But new research has introduced a compelling and entirely different suspect, one much closer to home: Saturn's own moons, especially the massive Titan. As Titan slowly migrates outward from Saturn due to gravitational interactions, its movement could be transferring angular momentum back to the planet, very gradually increasing the tilt of its axis. This is not an event from the distant past, but a process that could be happening right now in an astronomically slow motion. If this newer theory is correct, it means Saturn's tilt is not a fixed monument, but an evolving feature. The planet's lean might still be changing today, imperceptibly deepening over millions of years. This creates an active and fascinating debate. Is the tilt an ancient scar from a dance with Neptune, or a modern dynamic shaped by its own children? The answer reshapes our understanding of solar system stability. It forces us to ask whether giant planets are set in their ways after formation, or if their moons can actively remodel them over cosmic time. The angle at which Saturn meets the Sun, the very cause of its seasons and the dramatic shadow of its rings, might itself be a story still being written. Saturn's seasons unfold over a slow 30-year rhythm, and so too do its most spectacular planetary tantrums. Every Saturnian year, roughly every 3 decades on Earth, the planet's atmosphere erupts in a fury known as a great white spot. These are not ordinary storms. They begin as a brilliant, turbulent patch of upwelling ammonia ice clouds, a single bright blemish on the planet's golden face. But this blemish is a monster in its infancy. With astonishing speed, the storm begins to grow, stretching and spreading until it completely encircles the entire planet. Imagine a single thunderhead on Earth, growing so vast it formed a continuous, churning band around the entire equator, its head meeting its own tail. That is the scale of a great white spot. For months, this colossal band of convective chaos dominates Saturn's mid-latitudes, a stark white scar against the muted cloud bands, before it finally begins to fray, dissipate, and fade back into the background. The sheer power of these events is staggering, but the real enigma is their clockwork regularity. What internal timer, deep within Saturn, goes off like an alarm every 30 years to trigger such a planet-wide outburst? The storms seem tied to the seasonal cycle, as the northern hemisphere's summer reaches its peak. One leading theory suggests this is when Saturn's internal heat, constantly bubbling up from its deep interior, finds it hardest to escape. The upper atmosphere, warmed by the summer sun, may act like a lid, trapping the heat below. This pent-up energy builds and builds until it finally punches through in a single catastrophic release, a planetary-scale burp of heat and moisture that manifests as the Great White Spot. The fuel for this explosion is likely a vast reservoir of water vapor hidden deep beneath the upper cloud decks. When the convective plume finally breaks through, it lifts this water high into the cold upper atmosphere, where it freezes into crystals of ammonia ice, creating the brilliant white clouds we see. Another idea points to a slow, seasonal change in the depth at which water can condense in Saturn's atmosphere. As summer progresses, this condensation level may shift, eventually reaching a point where it triggers a runaway release of latent heat, powering the upward surge. It is a reminder that Saturn's weather is not just skin deep. These periodic cataclysms are a vital pressure valve for the planet's internal furnace, a rhythmic, visible heartbeat that reveals the dynamic struggle between the heat within and the cold of space. The Great White Spots are Saturn's way of breathing out on a cosmic scale, and we are left to wonder what other long-term rhythms and cycles pulse beneath its serene exterior, waiting for their time to erupt. These immense seasonal storms are a visible release of planetary energy, but Saturn also broadcasts its power in a form we cannot see. The planet is a constant source of strange and shifting radio waves, a crackling symphony known as Saturn kilometric radiation. This is not a quiet hum, but a powerful emission that can be heard across the solar system, generated by the frenetic dance of charged particles along Saturn's magnetic field lines. These radio waves are intimately tied to the planet's auroras, those shimmering curtains of light near its poles. Just as on Earth, Saturn's auroras are created when charged particles from the solar wind are funneled by the magnetic field into the upper atmosphere, where they collide with gas molecules and glow. But Saturn's auroras are also fueled from within by particles spewing from the geysers of Enceladus. This tiny moon injects a steady stream of ionized water vapor directly into Saturn's magnetic bubble, providing extra fuel for the light show and supercharging the radio emissions. The result is a complex radio signal that pulses with the planet's rotation, or so we thought. Here is where the mystery deepens to its core. For decades, scientists used these radio pulses as a clock, timing them to measure the length of Saturn's day. But this clock is broken. The rotation period you derive from the radio pulses is not constant. It changes over time, drifting by minutes over months and years. Even stranger, the clock in the North Pole ticks at a different rate than the clock in the South Pole. This is utterly bizarre. A planet's deep rotation, the spin of its solid core, should be a single, fixed number. How can the same planet have two different rotation rates broadcasting from its opposite ends? The leading theory is that these radio emissions are not a direct heartbeat of the core, but more like the voice of the magnetic field itself, and that field is slipping. Enceladus, with its constant geyser activity, may be loading Saturn's magnetic field with so much extra plasma that it is dragging the field lines, slowing their apparent rotation relative to the planet's interior. The different plasma densities or solar wind interactions at the North and South poles could then cause this drag to be uneven, creating the two mismatched clocks. It means we are not hearing the spin of the planet, but the spin of its magnetic field as it is encumbered by a fog of particles. This makes Saturn kilometric radiation a profound puzzle. It is a loud, clear signal that promised to answer the most basic question about the planet, only to reveal a far more complex and dynamic truth. The giant's true rotation remains hidden behind a curtain of noise, a secret kept by its own shimmering auroras and the relentless breath of a tiny, icy moon. That broken radio clock reveals a planet in constant, complex motion, but within the rings, smaller worlds conduct a more visible and intricate symphony. The shepherd moons are the master sculptors of Saturn's rings, and their work is far more detailed than simple herding. Moons like Pan, Daphnis, and Pandora do not just push ring particles into neat lanes. They use gravity as a chisel, carving out waves, scalloped edges, and breathtaking patterns on a scale of miles. Take Daphnis, a tiny moon only about 5 miles across. It does not orbit outside the rings like a border guard. It lives right inside one, traveling within the narrow Keeler gap in Saturn's outer A-ring. As it moves, its gravity pulls on the icy particles that form the gap's sharp edges. But it does not pull evenly. The particles closest to the moon get a stronger tug than those farther away. This difference creates a spectacular ripple. The ring material is pulled upward and outward, forming a wave that races ahead of the moon along the inner edge of the gap, and another that trails behind it on the outer edge. From a distance, it looks as if Daphnis is swimming through a calm channel, but its wake is not water. It is a permanent, undulating ridge of ice and rock that towers over a mile high. These are not simple bumps. Cassini's images revealed the waves have a complex, three-dimensional structure, with the ring material also kicked sideways, creating a scalloped, ruffled appearance along the gap's borders. The physics of a single, small moon creating such ordered chaos is a delicate balance. Daphnis's orbit is very slightly tilted and slightly elliptical. This means it does not move in a perfect flat circle within the gap. It bobs up and down and moves closer and farther from the edges as it goes. Each bob and weave imparts a different gravitational nudge, generating multiple overlapping wave patterns that interact with each other. The result is a constantly evolving, mathematically beautiful signature written in ice. The mystery deepens when we ask how these gaps stay so clean and sharp. Why doesn't Daphnis simply vacuum up all the loose material around it, growing larger or smearing the gap into a messy blur? The answer lies in a concept called orbital resonance. The tiny moon and the ring particles are in a synchronized dance. Particles that wander too close to Daphnis are not always absorbed. Instead, they receive a precise gravitational kick that pushes them into a slightly different orbit, often sending them back into the main ring or farther out into the gap. It is a game of celestial ping-pong where the moon acts as the paddle, constantly deflecting debris rather than collecting it. This maintains the gap's pristine edges. Pan, the moon that clears the famous Encke gap, performs a similar act, its gravity even creating a distinctive propeller-shaped wake within the gap itself. These shepherd moons are more than just janitors. They are artists and engineers. Their sustained, detailed work presents a complex, dynamical puzzle. How did they find their perfect orbits in the first place? Are they the cause of their gaps, or did they form within gaps that were already there? Their very existence and the exquisite patterns they maintain show us that Saturn's rings are not a passive disk of debris, but an active, vibrating system where every tiny world is a conductor in a gravitational orchestra, playing a silent, eternal song that shapes the rings one delicate wave at a time. There is a side to the rings we almost never see, a view from the deepest shadow. During its mission, the Cassini spacecraft performed a daring maneuver, slipping behind Saturn and turning its cameras back toward the Sun. For the first time, we saw the rings not by direct sunlight, but illuminated from behind by the faint, golden glow of sunlight reflecting off the planet's cloud tops. This perspective, from Saturn's own night, revealed a hidden layer of behavior in the ring particles. In the profound cold and darkness, the familiar bright bands transformed. Some regions, expected to fade into black, instead glowed with a soft, ethereal light. This phenomenon, called ring shine, was the first clue to a deeper mystery. The rings were not just reflecting Saturn's glow, they were behaving differently in the chill. Scientists realized that as the icy particles move from the day side to the night side, their temperature plummets by dozens of degrees in a matter of minutes. This sudden cooling changes everything at a microscopic level. On the sunlit side, a thin coating of frost might sublimate, creating a tenuous atmosphere of water vapor around each particle that helps keep them apart. In the shadow, that vapor instantly refreezes. The theory is that this rapid freezing acts like cosmic glue. The particles, now stickier and more viscous, may gently clump together into temporary, fragile aggregates. These are not permanent moons, but fleeting snowballs, constantly forming in the dark and then breaking apart as they spin back into the warmth and light of day. This transient clumping is a hidden rhythm, a daily cycle of assembly and dissolution happening on a scale too small to see directly, but whose faint signature is written in that ghostly ring shine. The mysteries here are profoundly subtle. What are the exact forces that make these particles stick? Is it purely the refreezing frost, or do electrostatic charges, built up differently in the cold, also play a role? How large can these temporary clumps become before Saturn's gravity or collisions tear them apart? This shadowy behavior forces us to reconsider the rings not as a static sheet of ice, but as a dynamic colloidal suspension where particles are in a constant state of delicate negotiation between sticking and scattering, governed by the simple, relentless turn from day into night. It is a reminder that even in the most studied places, a change in lighting can reveal an entirely new world of physics, playing out in silence on the dark side of a giant. This delicate dance of light and shadow, of particles clinging in the dark and scattering in the sun, points toward a final, overarching mystery that ties all others together. We have seen the rings sculpted by moons, darkened by dust, and showering material onto the planet. But these are not isolated events. They are pieces of a single, grand narrative, the life cycle of Saturn's rings. The ultimate question is not just how they behave, but what is their fate? Are we watching a permanent masterpiece or a brilliant but fleeting spectacle in the process of vanishing before our eyes? The evidence, when woven together, tells a compelling story of impermanence. The rings are too bright and clean to be ancient. The constant drizzle of ring rain, measured by Cassini, confirms they are actively losing mass to Saturn's atmosphere. Theoretical models that account for this rain, along with the darkening effect of micrometeorite bombardment and the gravitational nudges from Saturn's moons, all converge on a startling timeline. Saturn's rings may not be billions of years old. Instead, they might be a relatively recent addition, perhaps only 100 million years old, a structure that did not exist when dinosaurs roamed Earth, and their future is just as ephemeral. Current estimates suggest they could be completely gone in another 100 to 300 million years. On the scale of our solar system, that is the blink of an eye. This transforms our perspective entirely. We are not looking at an eternal fixture of the heavens. We are witnessing a cosmic event. Humanity, in this sliver of geological time, is privileged to see Saturn adorned in its full glory. This realization forces two profound and almost haunting questions. What did Saturn look like before the rings? For most of its 4.5 billion year history, the planet would have presented a stark, gas giant face to the universe, its complex cloud bands and polar vortices unadorned by that iconic disk of ice. And what will it look like after? A future so distant it defies imagination? Saturn will simply be a giant world, its rings reduced to a faint memory, perhaps a darkened trace of dust in its equatorial plane or a slight chemical anomaly in its upper atmosphere. The rings are a lesson in cosmic transience, a reminder that even the most stunning and seemingly permanent features of our universe are chapters in a story, with a beginning, a middle, and an end. We are here for one magnificent page. This grand narrative of creation and loss, of hidden oceans and screaming storms, brings us to the end of our journey through 25 of Saturn's greatest enigmas. From the geometric perfection of the North Polar hexagon, to the chaotic tumbling of Hyperion, from the youthful rings to the ancient tilted axis, each mystery peels back a layer of what we thought we knew. We have seen how a tiny moon like Enceladus can shout the potential for life across the solar system, and how the silent rain from the rings is writing a slow elegy for Saturn's most famous feature. Every puzzle, whether it is the missing methane or the broken radio clock, is a reminder that Saturn is not a static postcard. It is a dynamic, churning, and profoundly complex world, an ongoing experiment in physics and chemistry on a scale we are only beginning to comprehend. This collection of mysteries does more than catalogue curiosities. It maps the vast frontiers of our own ignorance. For every question Cassini answered, it revealed 10 more we had not even thought to ask. Saturn stands as a humbling and exhilarating monument to all we have yet to discover in our own cosmic backyard. The true legacy of these enigmas is the roadmap they provide for the future. What comes next? Our eyes turn to ambitious missions now on the drawing board. Imagine a drone soaring through the thick orange skies of Titan, navigating its methane rivers to finally land on the waves of Kraken Mare. Picture a dedicated probe, diving repeatedly through the plumes of Enceladus, equipped with instruments sensitive enough to detect the complex chemical signatures of biology. These are not dreams, but the logical next steps in a quest that has only just begun. The story of Saturn is far from over. It is waiting for the next chapter to be written by new spacecraft, by new generations of scientists, and by the simple, shared wonder of looking up at the night sky. Which of these 25 mysteries captured your imagination the most? Was it the hidden ocean of Enceladus, the timeless dance of the shepherd moons, or the haunting impermanence of the rings? Let us know in the comments below. And if you want to join us as we keep exploring the deepest secrets of our universe, be sure to subscribe for more journeys to the edges of our understanding. The cosmos is full of stories, and we have only just started to listen.